Hi, and welcome to another lesson about the x86 architecture. This time we are going to talk about the basic structure of this architecture. Objectives of this lesson. You will understand how programs are stored in memory and how they are executed by the processor. You will learn about the x86 32-bit registers. Storing programs in memory. The program to be run by the processor is written in memory, inside the RAM. I remind you that the RAM means random access memory. That is different, for example, from your hard drive. It's not that big hard drive that you have that has really lots of space. These days we have hard drives that are of size, maybe sometimes 1 terabyte. It's not that large. Usually you are going to have something like maybe 4 gigabyte of RAM or 8 gigabyte of RAM. It usually looks like those kind of long cards, long green cards. The memory is made of bits. Bits, just like we learned, zeros and ones. A byte is a set of 8 consecutive bits. A byte is the basic information unit in x86 processors. That means that the x86 processor or any processor that is compatible with the x86 architecture is going to work mostly with bytes. It is true that we can deduce or maybe change single bits. However, the basic information unit that is mostly used with most of the instructions is going to be 1 byte. Usually a byte will be represented as 2 hexadecimal digits, mostly because it is more comfortable than writing 8 binary digits. Hexadecimal digit represents 4 bits, is sometimes called a nibble. You might see this notion in some places, so it's important that you remember it. Some example for a simple program, just so you can get the feeling of how it works like. So, something like this. We just have a few bytes in here. Each of these is 1 byte. For example, 8 here is 1 nibble. Also 9 is 1 nibble. And together, 89 is 1 byte. I remind you also that this is all in base 16. The processor is going to look at these bytes and it will try to interpret them. In this example, the first 2 bytes, 89 and C1, are going to be interpreted as one instruction, which is going to look like this if we translate it to our language, maybe humans if you want to call it that way. At this point you might not understand this representation, the textual representation of the instruction. But mostly, if we just demonstrate for a moment, this first instruction, here in red, does some kind of data movement. It moves data from this location called EAX to this location called ECX. The next instruction that is encoded as 1 and then C9 actually means this instruction, which does some addition operation. And then there is the last instruction, which does another addition operation. We can see in this example that every instruction is of size 2 bytes, but this is not always the case. There are some instructions that are of different sizes. x86 instructions. An instruction in the x86 architecture represents some simple task. For example, addition, subtraction, moving data. And there are many more examples. You are going to see many examples for instructions in this course. Every instruction is encoded as 1 or more bytes. Instructions come in various sizes. There are very short instructions and very long instructions. Sometimes we are talking only about 1 byte. There are instructions of size 1 byte. And there are also very long instructions that sometimes even spend 10 bytes or more. The numeric representation of an instruction is also called opcode or operation code. The processor can only understand the numeric representation of the instructions. So for example, if we move back, this representation is much easier to read for me as a human being. But the processor is going to prefer this representation as numbers. The processor cannot read this. It doesn't have the capability of reading something like this. It can only understand numbers. So the processor is going to expect numbers as instructions. You don't have to remember the numeric representation of the instructions yourself. You are very lucky on this part. There is a textual representation for us humans, just like we saw in the last slide. Eventually though, you might remember some of the numeric representations of the instructions. Actually, I think that in the end of this course you are going to remember some of the numeric representations of the instructions. The processor's operation cycle. I tried to write here some kind of a very basic model of how the processor works. It is very simplified, okay, so don't take this literally, but mostly that's how the processor works, and maybe even almost every processor these days works somehow like this. So it's very basic. There are only 4 rectangles that we can see. The first one is read an instruction from memory. That's the first operation the processor is going to do. The next one is this, understand or decode the instruction. That means after the processor has read the instruction, it will try to understand what it means. For example, maybe it could be an invalid instruction and then it cannot be executed. So the processor is going to try to understand which instruction is it. After the processor finishes doing that, it is going to execute the instruction. That means if the instruction is about adding 2 numbers or maybe moving data, then the processor will add the numbers or move the data or do anything else that the instruction requires. Eventually, the processor is going to fetch the next instruction. That means it will go to the end of the current instruction and see what's next. It will see what is the next instruction. And then it will go again to read the next instruction from memory, and so on. We are going to speak now about a different subject, the registers. x86 processors have some very efficient internal places to store data. These are called registers. They are built inside the processor. So for example, they are not on the RAM. I remind you that the program is stored on the RAM, which is the random access memory. We spoke about this earlier. However, these internal places to store data are not on the RAM. They are inside the actual chip. They are inside the processor. Hence, they are very efficient. Also, they are very scarce. There are only a few. Together, they represent the internal state of the processor. Maybe you can call this the state of mind of the processor. It's like your own short-term memory as a human being. So the processor has something similar. Those kind of very small places that represent his current state of mind. As usual, these places are made of bits. That means that they can only keep zeros and ones. This is not very surprising. We will learn about the names of existent registers. Only later we are going to learn about the things that we can do with them. Don't worry if in the beginning you don't remember the names of all the registers. This is important. And now we are going to see some very strange registers, and since this is the first time that you might have seen something like this, you might be a bit scared because maybe you don't understand what's the point of all of this and what's with the strange names. So don't panic. It's okay that they seem a bit strange in the beginning. I assure you that in a few more lectures you are going to be very good with the register. So now you can just sit back and look at them for the first time, just to be familiar. The basic registers. Talking about the very basic registers, there are about 4. Each one is made of 32 bits. They are called EAX, EBX, ECX, and EDX. They also have a bit more special names. For example, EAX usually stands for the accumulator. The A in the middle between the E and the X means accumulator. EBX usually stands for base index. ECX is the counter, and EDX is the data register. In early x86 processors, every register had a specific job for a specific operation. In recent processors, mostly in protected and long modes, registers became more general purpose. The old roles of the registers can help you remember their names. You can learn from this that those 4 registers used to be very important for specific roles. For example, EAX used to be very good to add things, to add numbers and keep the result. And ECX was very good for counting things, maybe counting forward or counting backwards. But these days, mostly with the x86 for 32 bits and the protected mode, these registers are more general purpose. That means that almost each of them can do the jobs of the others. It is true that for some specific jobs, EAX might be faster than ECX. And for example, for some other specific jobs, ECX might be faster. But usually, you can just use them in the same way, and it's going to work. In very early processors, it wasn't the case. You had to use EAX for some stuff and ECX for others. And by the way, the E in those names stands for extended. Register extensions. The 32-bit registers are extensions of the old 16-bit registers. This is due to backwards compatibility. For example, talking about the EAX register, which is of length 32 bits. It is made of 2 parts. The high part, which doesn't actually have a name, and the lower part, AX, which is made of the lowest 16 bits of EAX. In the same way, AX is split into 2 parts, AH and AL. H stands for high and L stands for low. So AL is just another name for the lowest 8 bits, and AH is just another name for the next 8 bits. For example, if EAX contains this number ABCD1234, then AX contains 1234. If EAX contains this number, then the lowest part, 1234, is contained in AX. I remind you that these are just different names for areas in EAX. If I change bits here in EAX, they are automatically changed in here, in AX too, because AX is just part of EAX. In the same way, AH contains 12, because if we look at this number, the highest part, 1, 2, is what is going to be inside AH. AL is going to be the lowest bits, which is 3 and 4, exactly 2 nibbles. The same is true for the other registers. We just saw that this is true for EAX. This is also true for EBX, ECX, and EDX. Just in the same way. The only difference is this letter. You see, this A changes into B, and here this A changes into B, and so on. 64-bit extensions, also known as long mode. The 32-bit registers were later extended again to 64 bits. And it looks something like this. If we take the previous picture of EAX, it looks something like this. Try to remember how it looks like. The 64-bit case is just an extension of it. We can see the original EAX, which is split into AX and the higher part, and finally to AH and AL. And this EAX is only half of the RAX register, which is made of 64 bits. We are mostly going to deal with 32-bit registers in this course, but it's a good idea to always remember that if you wanted, you could work in the long mode, given that you have a 64-bit processor to work with. I have to say that in the long mode, mostly everything is very similar to this mode, to the protected mode of 32 bits that we are working in. I actually allowed myself to mostly work in 32 bits, because it might be a bit easier for you to learn the 32 bits part, and you can then easily upgrade to 64 bits whenever you want. So this is just to remind you that there are more extensions beyond the usual EAX that we are going to work with. Keep this in the back of your head. Almost every 32-bit register has a 64-bit equivalent, just like we see here. So for the rest of the registers, I'm not going to mention the 64-bit extension, but just remember that it probably exists. Some more registers. The index registers, ESI and EDI. ESI is the source index register, and EDI is the destination index register. Another very important register is the instruction pointer, also called EIP. Just like the other registers, those registers also have a smaller counterpart. For example, the ESI, made of 32 bits, has the smaller counterpart, SI, which is the lowest 16 bits of ESI. The same goes for EIP, which has the shorter counterpart, IP, which is made of the lowest 16 bit of EIP. Usually when we work in 32 bits, we don't get to work much with the shorter counterpart of these registers, but it does happen sometimes. Then it is good to know about it. Note, however, that in this case, there are no 8-bit counterparts. It only goes down to 16 bits, so it's not going that down. It's not going to 8-bit counterparts. I remind you how the EAX diagram looks like. You see here that it has the 8-bit counterparts. Not going to happen with SI or DI. Another register is the flags register. It doesn't have a very cool name as far as I know, but it is very important. We are going to talk about it in the future. And two other important registers that we are going to talk about are ESP and EBP, which are called the stack pointer and the base pointer. We are going to talk about them a bit in the future. There are even more registers besides the ones that I mentioned. There are even more. If we will have to deal with them in the future, then I promise that I'm going to explain them. But for now, working with these registers that were just introduced is going to give you a very good experience just by its own. When the time comes, you will probably see more registers, and you will also learn to appreciate them. Summary. Programs are just a bunch of bytes. We've just seen it. We've seen a few bytes that consist a program. The processor can read bytes and interpret those as a program. There are places to store data inside the processor called registers. They represent the inner state of the processor. Registers in this course are of size 32 bits, but I remind you that there are bigger registers if you ever want to work with them. Big registers are consisted of smaller registers due to backwards compatibility. Again, and I remind you, don't worry if you don't remember the names of all the registers. We are going to learn more about them in the following lectures. Thank you and see you next time.